Now, I'm aware that this video is dragging on already. We've covered the basic principles and all the different variants and so forth. I do, however, just want to have one more pair of questions, just because with projectiles they can throw some weird things at you, and I just want to make sure that you've seen the kind of things that you may have to face as well. So, to wrap up with, we also just take a look at these. Once again, we have the now recognizable projectile arc, that trajectory coming up from an elevated position A. And we now know what greatest height is again, like with that other question, we know that's 3 meters. And we have a point here that's T. Now, T is not on the ground, it's more like the B from the first question, but still, we're going to be looking at it. Yeah, we don't know U, and we don't know alpha. We're actually missing a fair bit of information. Now, all the same, we have to show, first of all, that U squared equals 2G over sine squared alpha. Well, the way we're going to go about this is to, once again, first of all, consider the vertical and consider the horizontal. When we're dealing with so many unknowns like this, it's good just to get as many expressions that you can generate as possible, and then maybe you can combine them together. So as I say, for this one, in the vertical, because we once again know this vertical height here, even though we don't know the distance across, we can say that the vertical displacement to begin with is going to be 1, because we're going from an elevation of 2 meters up to 3 meters. U is obviously not just going to be U, but it's going to be this component of the U, so it'll be U sine alpha. Well, just might as well have it. This one will then be U cos alpha. So yes, the U sine alpha. V, because it's the greatest height, is going to be 0. And A, we can say, is going to be minus G. Usually, yes, we would be 9.8, but because the answer it wants to show is in terms of G, we might as well just leave it as that. Therefore, putting this into like a V squared equals U squared plus 2AS situation, we end up with 0 equals U squared sine squared alpha plus, or rather now minus, because it's a negative G here, so minus 2 times the g times the 1, so just minus 2g. So if we add the 2g onto the left, we end up with 2g equals u squared sine squared alpha. And then just for the final step, you would divide through by the sine squared alpha, as you can see here, leaving you with the u squared on its own. Therefore, if you have shown what you had to show. Now that we have this, we'll have that the target t, so it's a target that something is shooting at, is 20 meters to the right of A and 0.5 meters above the ground. So actually, yes, we can now label some of the dimensions on here. So that's going to be 0.75 meters, and this here, all the way along, that is 20 meters. Now, find alpha, state a limitation of the model, and find the time of flight. Okay. So now, again, we're probably going to want to start by creating just some expressions in terms of your different vertical and horizontal components. If I actually just do that up here, just where we have space. So in the vertical, we can say that to get from A to T, to be clear, because that's a known endpoint again here. We would be going from a height of 2 meters to 0.75 meters, so that's a displacement of minus 1.25. Your u in the vertical is going to be that u sine alpha. The v we don't know. A would again be minus g, and t, right now we can just say it's t. We don't know what time it'll take. But we can say that in the horizontal, the time it takes could be found by distance over speed, if we rearrange the speed equals distance over time equation that way. So the distance that we're going to travel horizontally we know is 20, and then the speed is our u cos alpha. The reason why I suggest doing these like so is that obviously we want to create an equation somewhere which involves the alpha, and yet we also want to reduce the number of unknowns that we have. Right now, if we just try to make a surat out of this vertical one to begin with, we'd know none of the u, the alpha, or the t. Yet here, from the horizontal, we can get t in terms of that u and alpha. So while there's still unknowns, it's those same two repeated. So now, if we were to create a SUVAT from these, s equals ut plus half at squared, s is the minus 1.25, and that's going to equal, now ut, your u sine alpha times by what we know to be the same as 20 over u cos alpha. The u and the divide by u are going to cancel. And as well, from trigonomic identities, we can say that sine alpha divided by cos alpha is going to be the same as tan alpha. So together, that's just like 20 tan alpha. And then we'll have plus a half at squared. So the half of your a is going to be obviously, so g over 2, like half of your g. But then to times that by this as well, this squared. Well, this squared is going to be 400 over u squared cos squared. But then to have a half of that, that's going to halve the 400, bringing you back to 200 on top, so that it's so now it's a minus 200g over u squared cos squared alpha. Now, we can actually simplify this expression here further. We can get rid of this u to turn it all into the only unknown being alpha. So just on the left here, if we were to say that this would be the same as 200g over, well, we know u squared to be this, so it's your 2g over sine squared alpha times by your cos squared alpha. Well, the g's are going to cancel here. This 2 is going to cancel with this one again to bring that now down to 100. And also, when you have a fraction in the denominator of another fraction, you can bring its like mini denominator up on top, which would leave you as sine squared over cos squared. Again, the sine over cos is going to become tan, in this case, tan squared. So this now at the end becomes 100 tan squared, or minus that. So to bring things then onto the same side on the left, we would end up with 100 tan squared alpha. Now this will become a minus 20 tan alpha, and it's already minus 1.25, equals to 0. Therefore, we can just imagine this like a quadratic. You could replace the tan alpha with like x if you wanted, if it's any easier. But either way, you can either try to factorize this by scaling it up until it's all integers, or you can put this into the quadratic formula. And either way, you should find that tan alpha equals a quarter or minus 1 over 20. But when we then go further to work out what your alpha is going to be, so obviously alpha is going to be the tan inverse of whatever the fraction is here. If you did it with the minus 1 over 20, that would be an unfeasible angle in terms of this scenario. We need it to be an acute angle here, going in the positive, so it will just be the tan inverse of a quarter, which is approximately 14 degrees. Now then, as for the limitation is, you could say in this case, as well as anything like air resistance and so forth before, the limitation that's kind of more unique to this scenario is that the target is not a single point. Right? It's going to be something that's larger and in 3 dimensions. So there is a larger area over which you could still hit and get whatever point you're going for. Thus, there's going to be different angles of alpha that would nevertheless still hit the t. That's what the limitation is here, that we're assuming that t is only one very precise individual point. And lastly, to work out the time of the flight, well, time before we had as just being 20 over u cos a. Obviously just to get to t here, because we're not going to the ground. So we can say that t equals still the 20, but now that will be over. U is going to be the square root of what our u squared expression was, obviously. So we're going to have our square root of 2g over sine squared. We now know alpha is basically 14. And then that is going to be timesed by the cos alpha. Again, we now know alpha to be 14. So all of this in the denominator beneath 20, put that into your calculator, you get a time of flight of approximately 1.13 seconds. Okay. Now, if we're good with that, for the final time this video, just look to your own question. An archer shoots an arrow at 10 meters per second from the origin and hits a target at 10 minus 5 as coordinates meters. The initial velocity of the arrow is at an angle of theta above the horizontal. If g equals 10 this time, so they're giving you that because of saying it's going to help your equation, show that 10 theta minus 1 all squared equals 1, and then find the possible values of theta. Once again, I'll just suggest pausing the video and having a go for yourself. I will also suggest, as before, just trying to sketch this out for yourself, think what the implications are of this end position being given as coordinates instead of vectors as before. And yeah, just see what you make of it and press play again when you're ready to compare. Okay, so let's say that we're starting at the origin, so you've got some starting position here, and then the place we're going to end up is going to be 5 below us and then 10 to the right. So that's where the coordinate of 10 minus 5 would be relative to our starting position. I've done it this way round rather than going across first and then down, just because this is now more reminiscent of the examples that we have been having. Thus, once again, you'd have some trajectory. Because the angle is above the horizontal, we know it's not going down straight away. It's going to start going up and it's going to come down here, where we know that this initial speed here is 10, and that when we break this down here, that's going to be an angle of theta. Well, if we're going to be showing something in terms of tan, a tan that we don't have right now, we're going to want to start constructing things instead in terms of sine and cos, so that we can combine them together. Sine is going to appear in the vertical, so let's start by considering that direction. Because the only kind of distances that we have are from the start to the ground, we'll just say that your S is going to be the minus 5. Your U would therefore be 10 sine theta. We don't know what V is going to be. A, however, we'll say is minus 10, and we're using the 10 this time because the question has told us the gravity is 10. And then we're looking for time potentially. Not as guaranteed that that would be what we're looking for inherently, but because when we go over to the horizontal, if we're considering speed, distance, and time, well, the speed we're already going to know horizontally, or the velocity rather, and we know the distance, but again, time would be that unknown, and the time when it hits the ground is going to be the same both horizontally and vertically. Time is the key here. So time equals, so the horizontal distance here is 10, and that would be over the horizontal velocity of 10 cos theta, which is just 1 over cos theta. Now that we have this, we could substitute that into here, so we can say that this t will be that same 1 over cos theta. And with this, we can now construct an equation, which we need to introduce that equal sign we're trying to get to. So we can use S equals ut plus half at squared. So minus 5 equals the 10 sine theta over cos theta. And then that's going to be, well, plus half at squared. Well, a half of a is going to be minus 5, so minus 5. And again, t squared is going to be 1 over cos squared. So put that here. Now, This is going to be the same, if we were just to rewrite it slightly, as minus 5 equals 10 tan theta, and then minus 5 sec squared theta. Because if we remember from our identities, 1 over cos is sec, so 1 over cos squared is sec squared. But why would we want to do that? Why would we want to turn it in terms of tan and sec squared? Well, the reason for this is that we have a derived identity from one of the main identities. If you have that sine squared plus cos squared equals 1, we divide everything by cos squared. Well, sine squared divided by cos squared, that's going to be the same as tan squared. The cos squared divided by cos squared, that's just going to cancel out to 1 because anything divided by itself is 1. And then the 1 divided by cos squared is going to end up being sec squared there. Now, what's the significance of this? Well, what this means is that we can now replace the sec squared in this expression with an expression in tan squared, thus making this entirely in terms of tan, which is closer to the thing we're having to show. At the same time, we can also take the opportunity to just cancel through by a common factor of 5 if we want. So we could say that that would then become minus 1 over here. This will be 2 tan theta. And now here, obviously, this would also go to minus 1. So instead of minus 1 sec squared, so it's minus all of this. So minus tan squared theta and minus the 1. If we at this stage actually just swap the signs of everything, swap everything over the equal sign, so this is going to become a positive tan squared theta here and a minus 2 tan theta here and a plus 1 equals plus 1. This quadratic here can then be broken down into 2 brackets, or rather one identical bracket squared, that being your tan theta minus 1 squared equals 1. Oh look, that's the thing that we had to show. And it worked because we said that g was 10. If we had taken g as 9.8, we would not have been able to have simplified through by the same common factor above. Now, as for the other part of this question, to find the possible values of theta, well, we're now going to be solving this trigonometric expression here. So we'd want to square root to get rid of the square here. So your tan theta minus 1. When you square root, you have 2 possible answers. So it's either going to be plus or minus 1. Therefore, your tan of theta is going to be either 0 or it's going to equal 2. Now from here, if we were just to do that, okay, so theta equals the tan inverse of 0, well, that would equal 0 degrees. Or if we were to do that theta equals the tan inverse of 2, that would get us approximately 63.4 degrees. These are the 2 angles at which potentially this arrow would have hit that target there. However, because we know that it's above the horizontal, I know that with semantics you can argue that you're 0 degrees above the horizontal, but perhaps more practically we would therefore conclude that it would be the 63.4 degrees. Once again, I'm aware this has been rather long. Again, I just wanted to be thorough, make sure that we're happy with just the different kinds of variants on your projectiles questions. Hopefully this has cleared things up for you, and now you can go ahead and practice some more of your own.